Any of the others? Anything else?
36 on B.
B36. B36. An emergency supply of fuel fluid is often retained on the main hydraulic system reservoir by the use of a standpipe located at. What's a standpipe? Is it on the emergency pump, or is it attached to a reservoir? Does it attach to the emergency pump, or does it attach to the main system pump?
C.
Hold on. We'll find these questions.
I wasn't paying attention.
Okay. Here. The standpipe's always connected to the main system pump. The auxiliary pump or the emergency pump is at the very bottom of the reservoir. Okay. So that was 36. Anything else?
27 on Charlie.
27? 27. 27. Some gear type hydraulic pumps incorporate a feature which permits pump discharge fluid to be directed back to the pump. This feature provides for, should be for pressure loading.
And is that pressure loading the bearings?
It pushes on the bushings.
Okay. So it's just, I just didn't know the name of it. Okay.
46.
Hold on the picture, what we got. Yeah. A lot of the gear pumps have something, well, this is a Pesco pump anyway. What they do is they take the discharge of the hydraulic fluid, and then they've got a short bushing in the housing of the pump. The short bushing allows that discharge fluid to push directly on the bushings, and it loads the bushings against the faces of the gear. And I got maybe a better picture of that somewhere here.
So it's called pressure loading.
Yeah, it's called pressure loaded. So like in this case, they've got the discharge fluid. What some pumps do is they have a ability to put the head on a little reverse 180 degrees. So in that case, they've got two check valves. This one allows the discharge fluid to push past the check and then push directly on the bushing. So what it's doing is it's pushing on the bushings against the gear faces. The other feature that a lot of the pumps have is for another function that's called case pressure. We accumulate all the stagnant fluid from the clearances between the parts, and we expose that to a very weak spring check valve internally inside of the pump. This is usually no more than about 15 psi required to offset the ball, and then we divert that fluid back to the inlet. The purpose of that is to provide for cooling inside of the pump. So it's just an accumulation of fluid that causes that particular check to open.
So how come that question is pressure loading, not case pressure?
It's asking about pressure loading. 27C.
Pressure comes from.
Yeah, some gear pumps provide, it goes pump discharge fluid to be directed back to the pump. So here's the pump discharge being directed back to the pump. So you're pushing on the bushings, just like they're showing here. There's an annular opening in a lot of the pumps that provides for that. Yeah.
Number 46 on C.
46 on C. 46. 46 on C. 46 says, the diameter in microns of which the largest spherical particle will pass through a filter under certain test conditions define which filtration rating. That should be absolute. C.
It's wrong.
Did I get it wrong on
Yes.
that? Yeah. Circle it.
99.
You caught me. What do I got marked on the test as the correct answer?
B.
B. B. Okay. Should be absolute. Once in a while I blow it too.
32% of the test. On C. Question 25 on B.
25 on B. B 25. B25. What determines the minimum particle size which will be excluded by, or filtered by a Kuno stack disc edge filtration? You've got a series of discs and spacers. The discs are,
That's C.
I'm sorry?
That's 20,
Okay, so which question?
It's
25.
25 on B.
Oh, I'm sorry, 25. 25, a Warren hydraulic pump shaft seal can be normally detected by, they've got a seepage drain. There's a lot of pumps incorporated. They've got 4 ports that are mounted at the flange of the pump. And these are really seepage drain ports. When you see hydraulic fluid leaking out of there, that indicates that the shaft seal is busted.
So it'd be hydraulic fluid flowing from the pump drain port.
That would be it.
You have D marks on that one.
Let's see. 25?
I remember.
25
Oh,
should be
yeah.
C.
Yeah, it is C. Never mind. I'm reading wrong.
Okay.
Like at 26.
26. Okay, question number 26 on C.
Oh. So it's
On B.
on B.
B26. What determines the minimum particle size which will be excluded or filtered by a Kuno stack disc hydraulic filter? You've got a series of discs and spacers that are ganged on top of each other with a common rod. The spacers determine the degree of filtration. The discs separate it. So let's see if I've got for you. Here we go. You got a series of spacers and discs. The thickness of these things is really what determines the clearances that you have between the discs, and that's where the particles would lie. Okay? So they're razor thin, but nevertheless, that lets you control. What's the spacers?
B32.
B32. B32. BN32. B32. Service valves having a high pressure valve core should be A, the AN812 and the 6287.
I thought it was the MS289.
That one has no valve core. That one has only got a metal to metal seal.
But the 812 does not have high pressure in it.
They're all high. They're all considered to be high pressure service valves.
1500 was a low pressure.
They're all considered to be high pressure service valves.
Well, that's something they didn't.
Yeah. Sorry. But they have different features. Two of them have got have valve cores in them. Two of them also rely on a metal to metal seal, but there's only one that has both. And the 6287 has got a metal to metal seal, and it's also got a valve core. The 812 and the 6287 both have valve cores.
47C.
47 on C. 47. 47. Before removing the filler cap of an air pressurized hydraulic reservoir.
47 on C.
Oh, I'm sorry, I got B. Sorry. 47 on C. 47. The case drain of a variable displacement pump provides for heat exchange. The other type of drain that you might have on a pump is defined as being what we call a case drain. That provides circulation of hydraulic fluid back to the reservoir. A lot of variable displacement pumps will have 3 ports on them. One of them is obviously the inlet port that comes from the reservoir. The other one goes into the hydraulic system for the pressure manifold. But the third port goes back to the reservoir. That's what they call the case drain. And let's see if I got a picture for you. Speaking of that weak hole. Yeah, the seepage drain is different. The seepage drain that's on the flange of the pump, that's used for detection of a broken shaft seal. But when we're talking about a case drain, that's different. The case drain provides for usually going back to the reservoir. So like for example, here's an electrically driven pump, hydraulic pump, but that fluid goes back to the reservoir for cooling. And let's find, I think you got another picture somewhere here for you.
Number 20 C too.
20, which one?
On C.
C20. 20 on C. C20.
Last chance filter, wouldn't it be found in the reservoir too?
No.
Like this?
They've usually got either a micronic type filter or they've got maybe a metal mesh filter. The last chance filters are usually, they're micronic in nature, but they're usually positioned inside of servo valves and actuators. You'll never see them in the field. When they have to do an overhaul of like a power control unit or a servo actuator, that's where they're found. I think I got a picture of them, but not where they're installed. Hold on, 1 second. These are last chance filters. And again, you'll see them, they're buried. I've got they're wafer type filters in a lot of cases. I have a sample of one of these in the composite room I can kind of show you. They look like this in most cases. But again, they're called last chance because that's the last thing that the fluid gets to before it gets into like a servo valve. Which other one? Sorry.
3 on B.
3 and B? Sure. B3. What happens to the output of a constant displacement hydraulic pump when the hydraulic pressure regularly diverts the pump fluid from the system to the reservoir? Understand that the volume is still coming out of the pump, but what we've done is we've taken the discharge of that pressure and you're reverting it back to the reservoir. You're allowing no pressure to be built up. So that's why we've got an unloading valve. We're going to talk a little bit more about that in detail tonight. But with constant displacement pumps, you just can't stop the pump. What you have to do is you have to divert the flow somewhere. So here's an example of an engine-driven constant displacement pump. What they have downstream of it is the unloading valve. So in the kicked-in position for that unloading valve, the pump is actually seeing pressure and you're diverting flow through the unloading valve into the accumulator to build pressure. However, we can't stop the engine-driven pump. It's being driven through the accessory drive of the aircraft engine. So at some point, what we have to do is we have to divert the flow from the pump back to the reservoir. So what we've done is we've reduced the system or the discharge of the pump to 0 pressure, but the volume is still present. The volume is still coming out of the pump and it's just circulating back to the reservoir. Past this point, we've trapped the pressure past the unloading valve. So that's what they're getting at in the question.
21 Bravo.
21 on Bravo. 21 on Bravo. 21. Reservoirs may have a check valve installed in parallel with the vent to the filter. This is used on the Grumman aircraft, the landing gear mock-up that we have out in the shop. And they use it in vented reservoirs in order to allow a large slug of hydraulic fluid coming back to the reservoir to enter as easy as possible. The purpose of the check valve is to expel the air that's contained in the top of the reservoir. The filter acts as too much of a restriction to get the air out. So let me show you a picture. Some filters. Reservoir. It'll be in the vented section of them. If we can find it here. Here we go. So you got the reservoir positioned here. This is the filter that's in the vent line, so air can go through it, but not necessarily freely. Obviously, the purpose of the filter is to allow filtered air to get into the reservoir. Okay, that's not a problem. However, there's a big problem when you have a big slug of hydraulic fluid that's trying to get into the tank, get back to the reservoir. Whatever air is inside of here is going to impede that flow trying to get back. What we've done is we've installed a check valve that allows the air that's inside of this chamber to vent itself freely. So rather than try to fight it or fit through the the filter, which is a restriction, there's a pathway around the filter that allows the air to get out. So Grumman does it, other manufacturers do it too, I'm sure, but that's why they do it.
If it didn't have that, just put pressure on the pump.
The fluid just as, when you get back to the reservoir, what you're doing is you're now creating back pressure in the return line, in the return manifold. Because the return system, or the return portion of it, goes back to the reservoir. So what you're doing is you're now adding pressure into the return line, going back to the reservoir that you don't necessarily want.
43, see,
43 on C. 43. C 43. 43C. 43, self-displacing accumulators have how many chambers? They've got 4. It's a modification of a piston type accumulator that gives you a storage chamber that will work as a reservoir. It's got a vented chamber as well. And let's see if I can find you a picture. Okay. Inside of that accumulator, there's actually 4 spaces. They have a piston that looks like an H in cross section. They got a gas chamber that's pressurized, and again, just like a regular piston accumulator. They've got a high pressure fluid side, just like in a regular accumulator. Because the piston is kind of odd shaped, it's got an H shape, as the piston goes back and forth, there'll be a chamber that varies in size to accommodate fluid that works kind of like as a reservoir. And then one chamber that is really a vented area on the accumulator. To show you kind of a cross section, this is kind of what it looks like in 2 extreme positions. This shows you charged with hydraulic fluid against the gas charge. So when the hydraulic system was in operation, we built up system pressure. The fluid came in through the pressure port and it reacted against the gas charge on this side of the piston and shifted the piston this way. At the same time, what was happening, there's a vented chamber that's open to atmospheric air, but the return side of this piston has no fluid that's in it. If we use this as an accumulator in order to maybe make an actuator work or a hydraulic motor, you're going to be pushing this fluid out. It's got to go somewhere. So obviously with a regular hydraulic system, that fluid eventually goes into the actuator and is returned back to the reservoir. But some aircraft don't have a big enough reservoir to accommodate that fluid. So what they do is they route the fluid on the return side back to the cavity in the accumulator itself. So as the piston is being forced forward, displacing its fluid, the recovery of the return fluid ends up going into that chamber. Does that kind of make sense?
yeah.
Okay. So
I forgot about the vented.
that's okay.
What's on that photo you had before that has a screen on it? What is that screen?
Screen.
On the picture you had before this one, showing the accumulator.
Oh, it's a cutaway or something.
No, you used that.
We had it there, the blue one.
Yeah.
This one?
$3.99.
Go up to the top.
$3.99.
That one right there. It's like a cutaway or something.
It's a vent.
Oh, that's the bend part.
Well, maybe one of them is probably the pressure port on this side of it. I don't know. I don't have enough.
He's asking about the opening
That
right there.
screen.
Yeah, it's cutaway. You know,
That's like to show you what's inside there.
yeah, it's a cutaway.
Thank you, Joe.
Sure. What other questions you got? Okay. I'll fix the one of them. You got one of them, if you've got exam C, just circle number 46 if I marked it incorrectly. And that's it. Any of the others?
Just B47. B47?
B47. B47, what do we got? 47. Before removing the filler cap of an air pressurized reservoir, you better get rid of the air pressure in that reservoir. Okay, so correct answer should relieve the air pressure, A. On all of the pneumatically pressurized reservoirs, there's some method in order to remove the air before you remove the filler cap. On the Convair reservoir you have out in the shop, they've just got a poppet that's spring loaded. You push that poppet down, that releases the air pressure in the reservoir. Some Boeing aircraft have like a plunger, and what it does is just relieves the air pressure on top of the fluid before you open the cap. Any of the others?
13 on B.
13 on B. B13. After a hydraulic accumulator has been installed on the gas chamber charge, the main system hydraulic pressure gauge will not show hydraulic pressure reading. You got to get the accumulator charged with fluid. So this is the reason I brought the mocker, because sometimes it helps to kind of see what happens. We're getting up to get some fluid into the accumulator, and all we have to do is just operate the hand pump in order to send fluid against the gas charge that's there. Technically, the accumulator is charged. Is it charged to whatever value we want? No. But you certainly have got, you certainly don't equal the gas charge that's inside of the accumulator. What you've done is you've just added a little bit of fluid to it to get fluid inside of it. So it's technically charged. Okay. Any other questions? Anything? Okay, doke. Do me a favor, put your scantrons in your tests and pass them aside. And we're going to talk a little bit tonight about pressure control, both in regulation, and we'll also talk a little bit about unloading the pump in a lot of systems where that's necessary. I think we know that for hydraulic systems, we intend to build up hydraulic pressure. That's the name of the game. But obviously, if you have an overabundance of pressure, that's not good either. If you build up too much pressure, you'll have components that will fail. You reach the material limit for the strength of components, so either a line will burst, or an actuator will crack, or the shear shaft will fail on the pump. So we have to build up a certain amount of pressure. And good, they have some, but overabundance is not good at all. So what do we do in order to kind of control pressure? Well, I'll show you a few different things that we can do. And let's see what we can start at here. Let's start right at the very beginning. Let's look at a really simple hydraulic system. Well, you got a reservoir, you got an engine-driven hydraulic pump, you got a device that's called a relief valve, and downstream of it, we've got hydraulic pressure that's being developed in the line going to selector valves. When you operate a selector valve, what you're doing is you're diverting the flow of hydraulic fluid into an actuator. At the same time, when the handle has been positioned one way on the selector, the fluid that's on the other side of the piston is being sent back to the reservoir through the return manifold. So, okay, no problem. What's controlling system pressure in this case is a relief valve. In its simplest form, it's really nothing more than a big ball under a big compression spring. So what's happening is the fluid is coming in and seeing the ball of that relief valve is pushing against the ball and compressing the spring, and we're fighting that relief valve in order to develop system pressure in the line. Any pressure or any fluid flow that the pump is producing, fluid flow that's coming from the pump, in excess of that is being diverted back to the reservoir. So we're holding a particular pressure in this pressure manifold monitored by the gauge simply by allowing a certain amount of fluid that's being forced by the pump discharge in order to build pressure in the line. Anything in excess of that is being sent back to the reservoir. Understand something very important for the illustration. The pump is fighting to keep that relief valve in kind of a position of partially open because you're compressing the spring against the ball. So the pump is fighting. Is this okay? The answer is maybe. If it's a low pressure type of system, it's not going to produce a tremendous amount of wear on the pump. For example, we use something very similar to this to control the pressure for a constant speed propeller. Many propellers, constant speed props, have a governor that is used to control the pressure that's required for changing the pitch of the propeller. And it's pretty simple, but understand the pressures that are required for changing pitch on the prop using engine oil as the method or the fluid for changing the pitch of the prop. You know, you're talking maybe 150, 200, or maybe 300 PSI that you're trying to control. But obviously, if you're trying to establish a pressure downstream of that relief valve of maybe 1,500 PSI or 3,000 PSI, that's not a very good method of controlling pressure because the pump is working against that relief valve to hold itself open. You kind of see what's happening? So the pump is eventually going to wear itself out. So what I'm trying to tell you is if you're just establishing a low amount of pressure, maybe no harm or no foul on the pump because, again, the pressure is not significant enough in order to really damage the pump in the long term. However, to try to do the same thing where you're trying to build up and hold a whole bunch of pressure, no, that's not going to work. Eventually, the pump is going to fail and the relief valve is going to chatter itself to death, opening and closing, in order to try to control that system pressure. So again, for a very simple system where the pressure is kind of controllable to a low degree, a low amount of pressure, okay, fine. And again, the example that I would use would be a constant speed propeller where we're trying to control the oil pressure used to vary the pitch of the prop to, you know, whatever angle we want. Okay, fine. Right, we got a relief valve in the circuit. But it doesn't certainly unload the pump. The pump, even when the relief valve is controlling pressure, the pump is fighting to keep that relief valve throttled to a partially open position, all right? Well, this is what they used to do in the old days in order to make actuators work and control system pressure. They had a system that they call a direct pressure system. What they've done is they've installed a plunger type of valve that they call a power control valve. And used with it is another device called a surge cylinder. This is a semi-automatic method of controlling system pressure. When the power control valve is in its open position, fluid flow from the engine-driven hydraulic pump just circulates naturally back to the reservoir. However, when you want to build up system pressure, the pilot or somebody in the crew has to push on the plunger, this power control valve. What that does is it blocks off the return of the flow back to the reservoir, and now the fluid under pressure is forced to go through the relief valve and also into the selector valve to make the actuators work. At some design pressure, this power control valve poppet or plunger will pop itself back out again, and then the flow is established back to the reservoir. So that's why I kind of call it semi-automatic. It requires some attention by the crew or the pilot in order to make the actuators work. What's the advantage of something like this? When there's nothing that has to be actuated, the flow from the pump just circulates back to the reservoir. This requires an intentional motion by a crew member in order to block off the reservoir by pushing the poppet in. When the pressure builds up to a design point, the hydraulic pressure that we build up then pushes the poppet back out again, and then the flow is delivered back to the reservoir. So semi-automatic. Not an ideal way to control pressure because obviously you have to remember to do something if you want to make these actuators work to build pressure. You're going to first have to push the plunger in the power control valve and manipulate the selector valve that you use to operate the actuator to make it work. When the actuator goes to full travel or the pressure builds up to a design point, then okay, it pops itself back out again. What you need to know too is these early systems require a help. The helping device that you need with it is a surge cylinder. There's a piston under a big spring inside of here. What that does for you is it prevents that plunger from prematurely popping itself back out again to the open position. So maybe if a surge of hydraulic pressure is developed that surge isn't felt directly by that power control valve. It first has to work against a spring and a piston inside of here in order to be able to kind of modulate or kind of control the pressure to a degree. So it works kind of like a capacitor in an electrical circuit. I guess is in a simplest idea of how it might function, works like a spring accumulator. So the spring is kind of pushed back against the piston as the pressure kind of builds up, and it prevents this thing from prematurely flipping itself back to the open position where deliver flow back to the reservoir. The thing that we also need though in the circuit, let's say for example, the pressure builds up and for some unknown reason this thing fails where the plunger has been pushed in, we're still going to have a relief valve in the circuit that's going to send the flow back to the reservoir if in fact this device doesn't revert itself back to the open position. All right, so we use the relief valve as a standby device or as a safety device in this case. So again, this is our method of controlling the discharge pressure, but also an important thing too is it's designed to unload the pump. When the valve is open, this power control valve is open, the fluid flow that comes from the discharge of the pump is free to circulate back to the reservoir. This makes life much easier for the pump. The pump probably won't fail as soon as other types of systems where we just build and hold pressure. So far better than having just a relief valve kind of modulating itself open and closed to control pressure because the pump never gets a break. Does that kind of make sense? All right. There's an FAA test question that is kind of an obscure question that still asks about this type of system. And they want you to be able to adjust this system or adjust the relief valve for its opening point. Well, obviously, if you had to adjust the relief valve for the point at which to open at, you're going to have to manipulate this valve and hold it in the closed position, and then take a look at the system pressure gauge to figure out at what point this valve is going to open at. So obviously, this device opens at a lower pressure than the relief valve is set to open at by its very nature. You're going to have to use this as a safety device. But in order to be able to tell it what point this valve opens at, we're going to have to momentarily disable this device by holding the plunger in. When we hold the plunger in and hold it, and physically hold it, we build up enough pressure to allow the relief valve to open, and we can verify its point of opening by looking at the system pressure gauge. So the FAA test question, it says, adjust pressure relief valve with a power control valve held in the closed position. So again, you're going to have to hold this in the closed position and keep your hand on it. We're going to then allow the pressure to build up to the point where the relief valve opens. You can see that pressure by looking at the gauge in the circuit. Does that make sense to you?
Yes.
Question?
Watercraft, do you have any examples of a system like this in an aircraft?
Old. I mean, you're going to have to go back to the 1930s.
Okay.
I mean, really old. And it's too simplistic to use for modern aircraft.
Right.
Even those aircraft that were built in the mid 1940s. You got one or two hydraulic components you're trying to make work, and that's about it. Okay, but if you've got multiple components, we don't want to have to use that power control valve in order to kind of control pressure. We want something that's better for control pressure and to unload the pump as well.
Like an unloading valve.
And unloaded valve. That's where we're going.
Is there a spring that works against the plunger?
Yes. If you want to see a close-up view of it, you've got this picture in your fluid power book. This is one reason why I use that fluid power book, because it covers some really obscure things. This is a picture that I stole directly from it. What it's got inside of it is it's the plunger. They show you in both positions. The system pressure has to work against this poppet or plunger. It's really got a spring on top of it that kind of holds it in one position. So when the pressure kind of builds up, what it does is it pushes the plunger out, and then the fluid flow from the pump is directed back to the reservoir. In its closed position, what you're doing really is just blocking the reservoir. That's what you're doing. But understand, this device is not enough to guard you against a spike in pressure. You're going to need also a surge cylinder. And I don't know if your fluid power book has got a picture of this, but I stole it from another text. This has just got a big spring in it with a piston. So what it does is, it kind of works to prevent this thing from switching to the open position too quick. So a surge of hydraulic fluid is developed, it kind of holds it in the closed position. There used to be a really obscure FAA test question that would ask you what the purpose of that power control valve was, and it says the hand shut-off valve with an automatic turn-on feature. And really what it does is it shuts off the reservoir and then it automatically turns back onto the reservoir when the pressure builds up. But that's the purpose of the power control valve, right? Does it unload the pump? The answer is yes. Is it completely automatic in operation? No. Okay. So it allows us to develop a particular pressure. It does in fact unload the pump, but it's not automatic. What's a better thing? Well, we're now going to use a device that's pretty much all automatic. We're going to use a device called an unloading valve. We're still going to have a relief valve in the circuit in order to work as a backup in case the unloading valve fails to go to a position called kicked out. But we're not going to be damaging the pump by continually having back pressure being felt at the discharge of the pump. Once we build up pressure, the unloading valve is going to sense that pressure and will divert flow from the pump back to the reservoir. So you take a look at it, you've got all the components that you had before, but maybe a little bit more sophisticated. You've got a reservoir, you've got the same engine-driven pump, you've got an unloading valve, and the unloading valve works similarly to the relief valve, except the unloading valve is called an unloading valve because it takes the back pressure off the pump discharge once the system pressure has been built up downstream. So at a certain point, the fluid flow is going to go through the unloading valve, and unrestricted, it's going to find a path back to the reservoir. So it's automatic. We're still going to need a relief valve in the circuit. The relief valve is a backup. If the unloading valve should fail to divert the flow back to the reservoir at the correct period or correct time, the relief valve will control system pressure. But notice also something too, that relief valve does not unload the pump. When the unloading valve has failed, the relief valve will control system pressure to a value above the unloading valve point of pressure. However, the pump is fighting to keep that relief valve open. So it's just meant as a stopgap measure necessary to a point where we can replace the unloading valve. But we need it. We need to have that in the event that the unloading valve fails. Okay. All right, so that's kind of where I wanted to go. Even before we kind of get there, I was, during your exam, I had a chance to take a look on YouTube, and I didn't really have an opportunity to take a look at or listen to the audio that's being presented. But maybe just something really simple on relief valves, on what they do. Let's just take a look at this real quick.
Bite-sized industrial training. Hello, this is Carl at lunchboxsessions.com. In this video,
Hello,
we're
Carl.
going to look at basic functions of a very important pressure valve called a relief valve. Many hydraulic systems use a pressure relief valve as the primary means to limit maximum system pressure. Without a relief valve in place, pressures could potentially build to an excessive level where the machine might be damaged or perhaps a hose might burst, endangering human lives. The type of relief valve we will be examining is the simplest style with only one poppet and one spring. It is known as the direct acting relief valve. This live schematic shows a fixed displacement pump sending a flow of 10 gallons per minute through the system. Our directional control valve will remain energized in the cylinder extend position. The relief valve is shown in cutaway form so that we can see all of the details and actions of the relief valve as it responds. The system pressure is indicating 200 psi, which is calculated by looking at the mass being lifted, 2,000 pounds, divided by the 10 square inch surface area on the bottom of the piston. The controls show that the relief valve is set to 300 psi. But how do we know this? The only true way to know the relief setting pressure is to observe the system in action and the values on the system pressure gauge. Let's add a 2,000 pound brick for 4,000 pounds total divided by 10 square inches, and we did not achieve 400 psi. The cylinder crashed back down to the bottom, and the maximum pressure on the system gauge indicates 300 psi. When flow from the pump can take no other path than through the relief valve, the pressure value on the system gauge then indicates the true setting of the relief valve. Let's add 3 more bricks for a total of 10,010 pounds. We would need to trap a system pressure of 1,001 psi to lift this load. Now, if we tension the spring on the relief valve, we notice that the system pressure is climbing as the relief valve poppet pushes against the flow. As the relief valve can only be adjusted up to 1,000 psi, we are unable to lift the load on the cylinder. We simply cannot trap the required pressure in the system. Watch what happens as we remove 1 brick for an 8,000 pound remaining load divided by 10 square inches for 800 psi system pressure. The cylinder starts to lift, but notice that the relief valve is not closed. Let's once again add a brick and remove a brick while watching the poppet in the relief valve. Removing a brick allowed the poppet to advance upward, but the relief valve does not quite close. Removing 1 more brick for 600 psi system pressure, we see that the relief valve has closed completely and that the cylinder has increased speed. Again, let's add the 4th brick and remove it while watching the relief valve and the cylinder. Remember that the relief valve is set to 1,000 psi, but clearly the valve opens at 800 psi and begins to direct at least some of the system flow back to tank. In this case, the cracking pressure is 800 psi, where the relief valve setting is actually 1,000 psi. The difference between the cracking pressure and the setting pressure for this particular relief valve is 200 psi. In order to lift the system at maximum possible speed with an 800-pound load, the relief valve would have to be set a little higher than 1,000 psi. In future videos, we will examine pressure override in more detail and look at more complex relief valve designs.
We have hundreds of
This is kind of important to note too. Regardless of that relief valve setting, if you've screwed the relief valve spring all the way in, the pump is under load. So again, you're not really controlling the discharge of the pump to the point where the pump is unloaded. So if you put a lot of compression on that spring, whatever pressure you build up in this line might be enough in order to actuate or make the actuator move. But understand that pump is working against that relief valve to hold it open. So you may be sending fluid back to the reservoir, but the discharge of that pump is not helping it. So it eventually will cause the pump to wear out. So this is the reason why we need to have an unloading valve in the circuit. Y'all kind of see that? Yep. Okay, all right. All right. All right, so, okay, here's a more sophisticated system that we might have. You've got an unloading valve that's in the circuit that's designed to unload the pump. You've got a system relief valve that works as a backup in the event that the unloading valve fails to control pressure. And we've also got other valves that are called thermal relief valves, they're abbreviated as TRVs. And they're kind of like miniature system relief valves, but they're designed to protect the actuators. And I got to remember to raise the board. So if we were to do something like this, you can kind of envision what's happening with the relief valve. Simplest form, big spring against a massive spring against the ball. The unloading valve is much more complex. There's a balance of pressures and forces that are used internally. In one particular position of the unloading valve, the flow from the reservoir goes through the pump and in through the unloading valve, and then begins to build system pressure by confining the fluid inside of the pressure manifold. So this is the position of the unloading valve that we call kicked in. So in this position, the flow from the pump is being diverted into the pressure manifold, and we build it up to a certain point. The other point that the unloading valve has is called the kick-out pressure. And when the kick-out pressure, what we're going to do is we're going to divert the flow from the pump up this way back to the reservoir. Past this point, past the check valve in the circuit, you're gonna hold pressure in the pressure manifold and in the accumulator. But what this has done for you is it's now unloaded the pump. So now the discharge of the pump is circulating back pretty much unrestricted. And this is desirable. It'll prolong the life of the hydraulic system and particularly the pump. So it's not like using a big spring and a ball in order to control system pressure. You're working internally against components or component piece parts inside of the unloading valve to hold the unloading valve in the kicked out position. In addition to it, I want you to kind of take a look at the picture as well. There's a helpful device that will hold that unloading valve in the kicked out position. And I think you can guess what it is. It's the accumulator. The accumulator works just like a battery in an electrical circuit. So let's assume we're in the kicked out position and we've got flow going back to the reservoir from the pump. You've now built up pressure in the pressure manifold. When you operate a selector valve, what you're really doing is you're bleeding the pressure out of the accumulator, and then you're making the actuators work. The fluid flow comes out of the accumulator into the pressure manifold, and then the actuator works. The displaced fluid from that pressure manifold goes eventually back to the reservoir. But really, you're using the accumulator in the circuit in order to do that. It's like a battery in an electrical circuit. Eventually, you pushed out enough of the fluid in the accumulator where the unloading valve sees that as a drop in pressure. And at that point, the unloading valve now replenishes the pressure in the accumulator and go back to the kicked in position. Eventually, the unloading valve will go back to the kicked out position once the pressure has been built up. But this is a desirable feature of what we need to have. We need some kind of stabilizing device that prevents the unloading valve from switching back from kick in to kick out too frequently. So it prevents the accumulators really helping to prevent the unloading valve from flip-flopping back and forth from kick in to kick out, kick in to kick out too quickly. So again, just like you have a voltage regulator in an electrical circuit with mechanical relays that are, 3 relays that are inside of it, this does the same thing. What it does is it prevents this unloading valve from working itself to death. So, okay, so this is what we have. Okay, it's the TRVs, the thermal relief valves. The thermal relief valves are a miniaturized version of the system relief valve. If the selector valves are in the off position, and this is a closed center hydraulic system, there's the potential that fluid that's trapped in the what we call alternating lines or inside of the actuators, they'll begin to thermally expand. If there's a source of heat energy that's next to the actuator, that heat will cause the liquid to expand. And if there's nowhere for it to go, the pressure builds up beyond the extreme point. So what we have to do is we have to vent that fluid out. So what we do is we have a valve, it's called a TRV, and really all it is just another tiny little ball but getting a really heavy spring. And the idea is that the fluid should thermally expand. All it takes is just a drop of fluid to go by the valve and the pressure will subside again. But it's a necessity. If the valves are in the off position as they are now, there's no natural return path for that fluid to escape. So what we need to do is we need to incorporate those devices as protection for the alternating lines and also for the actuators themselves. The landing gear mock-up that we have out in the shop, that Bremen, it's got several TRVs that are on them. But again, it's a necessity. Remember also too, it really isn't directly pressure. It really is, although they're called thermal relief valves, it isn't really heat directly that's causing the valves to open. It's the consequence of pressure buildup as a result of fluid expansion from the heat that makes the valve work. Does everybody kind of see that? All right. Also note too, once the valve vents just a drop of fluid back to the pressure manifold or the return manifold, the valve just shuts itself off, just like the relief valve does. If you were to kind of freeze frame the system relief valve, if the unloading valve had failed, let's say that this thing is stuck in the kick-in position, this thing is going to be chattering itself to death because it's a slug of fluid is going to be going by it, the pressure goes up, the spring compresses, the ball comes off of its seat, the pressure subsides, the ball comes back on its seat, and the process repeats itself so repetitively that eventually the relief valve is going to wear itself out. But again, the system relief valve, it's a stopgap measure in the event that the unloading valve sticks in the kicked-in position. We have to have it. So, okay, that's how it works. I've given you some generic values for operation of the system as well. There's usually a range of operation for the unloading valve that's designed to kind of work in. So let's say we've got a kick-in pressure of maybe 800 psi. So once the pressure goes down below 800, the unloading valve will go to the kick-in position in order to build pressure back up. And we've got what we call a kick-out pressure of maybe 1,000 psi. So the unloading valve kicks out at 1,000 psi, but the pressure's got to drop in the line to maybe 800 psi before it goes back to the kicked-in position. So we've got a differential of maybe 200 psi. So it's about a 20% difference in pressure between the two. The relief valve is designed to open as a backup. So its point of opening has to be higher than the kick-out of the unloading valve. So in this case, we might have maybe what we call the cracking pressure, the very point at which the relief valve opens at. We might have this thing set at maybe 1,200 psi. It's about 20% higher than what we had for the kick-out of the unloading valve. But again, by its function, it has to be sent to open or crack itself open at a pressure higher than the kick out of the unloading valve. So again, about 1,200 psi. The thermal relief valves, even higher. You might find that if the system pressure is designed to be established at 1,000, you might find that the TRVs are designed to open maybe at 1,400 or 1,500 psi each. Okay, so again, that's kind of how the circuit has to kind of work. Questions? Any questions that you kind of have? So just to kind of verify that you know what's going on. The unloading valve, it unloads what component? Does the relief valve control system pressure? The answer is yes, it could. But does the relief valve unload the pump? No. Okay. So when the relief valve is controlling pressure because the unloading valve has failed, the answer is no. It will control pressure to a higher value, but it does not unload the pump. And that's really the important thing with high pressure systems. We have to find a way to control the discharge of the pump. Okay. What do they do on electrically controlled systems or electric pump systems? What they'll use is a pressure switch in order to kind of control the pump. But it's done indirectly. Really, the pressure switch is the pressure builds up, cuts off the electric motor, and then that controls system pressure. Will they still have a relief valve in the circuit in order to make it work as a backup? The answer is yes. So again, if the switch contacts on a pressure switch fail in the closed position, you're still going to have something that will control the ultimate system pressure. Would that relief valve really work for a long period of time? The answer is no. It's a stopgap in the event that just to prevent the system from blowing itself up. So that's it. Okay. All right. Let's talk about different types of unloading valves. You are probably never going to see this particular type of unloading valve. It's a purely mechanical type of unloading valve. It's got a lot of piece parts that are in it. It's considered to be too complex by today's standards. But this shows you kind of what they use as the internal piece parts of that mechanical type of unloading valve. You've got a plunger or a piston inside of it that sees system pressure. You got a big spring behind it that the system pressure has to work against. You've got a check valve that isolates the reservoir and traps system pressure on one side of the unloading valve. You've also got a cam, and you've got a high spot on the cam, and the cam is loaded against a follower with a spring on the other side of it. And there's the pivot point for the cam is located here. This position of the unloading valve shows you what they call, again, the kicked out position of the unloading valve. What that means is we've trapped pressure in the accumulator. Any flow that's being delivered from the pump is being diverted back to the reservoir. So we've got a flow path that comes in from the pump. It goes around this valve that they call a bypass valve, and it goes back to the reservoir. Until the pressure drops off behind this piston enough we're going to continue to retain the, or at least deliver, or have the flow being sent back to the reservoir. If the pressure drops off in this line, the spring pushes the piston back, and what will happen is this cam is going to be now positioned on the other side of the hump, of the high spot. This little connecting part that they have attached to the spring will ride over to the other side of it, just like you see over here. And what happens then is we'll go back to the kicked in position. So that what we'll do is we'll deliver flow from the pump in through this line, through the check valve, and into the system in order to build pressure up again. When the pressure reaches a certain point, it's enough to push this poppet or the piston back. It causes the cam to now flip to the alternate position like you see it here now, and then we go back to the kicked out position. There's really two springs that are inside of here that control really the, against system pressure. You've got a big surge spring. You've also got another spring against the cam that kind of controls the reactive force against the system pressure. And there's a small amount of adjustment that can be made. If you get an adjusting screw over here, obviously if you put more pressure on the screw, it takes more pressure, or you're putting a preload on the spring, it takes more system pressure to overcome that. You'll cause the kick-out pressure to rise. So it takes more pressure, or I should say more pressure in order to offset it to kick out. The control of how fast the positioning goes from kicking to kick out is really controlled by the cam spring down here. So it rides against the follower, and again, it controls what they term in the book the liveliness of the device, or its ability to kind of shift from one position to the other. But this is what we have for a mechanical type of unloading valve. Again, probably never seen one. We've only seen an illustration in the book. Does it exist? Yes, but kind of rare to see it. More commonly, what you'll find in an unloading valve, let me cut right to the chase. This shows you a generic version of a balance type pressure regulator. The Vickers unloading valve that we use in the shop for the checkout, it has this type of feature for its operation, but they show you a simplified view of what's happening in the unloading valve. This works by a difference in surface areas against the prevailing pressure. So what they've used is they've used common, or at least values for surface areas that make it kind of easy to understand for how it works. What they're telling you is that for pressures underneath 800 psi in the system circuit, the unloading valve will stay in the kicked in position. So what we're doing is we're allowing the flow from the pump to go past an internal check valve inside of the unloading valve, and then the fluid flow from the pump is being diverted into the accumulator. As we begin to build pressure, you'll have a pressure that's forcing this piston up. But what they're telling you is until we reached about 800 psi, there's not enough pressure or force in order to compress the spring. So we continue to build pressure. Okay. What's also happening at this time as well? So the pump is displacing fluid into the accumulator. The fluid flow from the pump at whatever pressure is created at a given time is also working on the surface area of this exposed ball that's inside of the unloading valve. So what we can kind of take a look at is this. We've got a certain force that is holding this ball down on top of its seat. We've also got another force that is pushing down as well, which is the spring. We've got another force which is really working this way against the piston. So we have one force pushing down against the ball. We got another force which is the spring pushing down. We've got one force that is pushing up against the piston. Well, look to see what happens in this case when pressure goes up above a certain point. You've now got more force pushing up than you had pushing down. So in this case, what happens, let's just assume we get right to 800 psi. You've got 800 psi that is pushing up on top of the piston. The spring was worth a force of 600 pounds, but you can kind of take a look at what was happening over in this position. This has got a surface area of 1/4 square inch. What's 1/4 of 800? How much is that?
200.
200. So here's 200 pounds of force. Here's another 600 pounds of force. And we'll assume that we've got a total of 800 pounds that is pushing down. In this case, you had 800 pounds that's kind of pushing up. So it's kind of balanced. You're right at the teetering point of this thing, kind of going to the kicked out position. As soon as you get to a slightly higher amount of pressure, what happens is the piston is pushed up, the ball has been pushed off of its seat by this rod, but most importantly, you've lost the force that was holding this ball down against the seat. The fluid flow that was coming from the pump has got a way to pass around the ball and circulate back to the reservoir unrestricted. So now you've got a flow path that's going back to the reservoir and you're in the kicked out position. Well, when will the unloading valve go back to the kicked in position? Well, we would have to drop the pressure in this chamber in order to allow this ball to come back down. But here's the interesting thing. In the picture that they're showing you for kicked out, you don't have any force that's pushing down on top of this ball. So you've got 800 pounds per square inch that's pushing up against 600 pounds that's pushing down. So I would ask you, what pressure would it have to drop off to in order to go back to the kicked in position? 600, very good. So even though we've got a 800 PSI that's been trapped in here, what you've done is you've unbalanced it to the point where you've now taken the force off of the ball, and now, again, the pressure would have to go drop below 600 PSI before it goes back to the kicked in position. Do y'all kind of see what's happening? The check valve closing, you've got more pressure on this side of the check valve than you have over here. You've got maybe 800 PSI of pressure in the accumulator that's holding the check valve shut. The very point at which the ball comes off of its seat, it'll cause that check valve to immediately slam shut. So it'll hold itself in the kicked out position. What other component downstream of this is going to help you to hold that pressure in the system? The accumulator. So when the pressure drops off to 600 PSI in the accumulator, or below that anyway, the piston will come back down again, and then it'll go back to the kicked in position. So this is really the essence of what's happening in any type of balanced accumulator. You're working against surface areas that are in check against each other. In this case, you've got 800 pounds on one side of the piston balanced against a combined force of 800 pounds on two items. And when we go to the kicked out position, well, you now somewhat unbalanced it to the point where you've got more force on one side of it than the combined force trying to push it back down again. Do y'all kind of see what's happening? Okay. All right, so that's the kicked in and kicked out position. And again, that differential, in this case, 600 to 800, that 200 PSI, again, what helps you to hold that is really, for an extended period of time, is really the accumulator that is mounted downstream of the unloading valve. Another picture, this one came out of one of the military manuals, but they didn't assign any generic values to the surface areas or the tension or compression that you have on the spring, but again, you can kind of see how it works. Here's another one, same idea. This one shows you a check valve, but in many cases, the check valve is integrated inside of the unloading valve. And in the kicked out position, the check valve will be closed. The Vickers unloading valve, this is what we use in the shop for the checkout, and it shows kind of the component parts that we have on the inside of it. You're still working against surface areas in order to go from kick in to kick out, but it's not really apparent. When you take a look at that generic picture that I just showed you, you can kind of easily see again your balancing forces. But the same thing is kind of occurring inside of the Vickers unloading valve. What you have for component parts inside of it, you've got what they call a pilot valve spool. This thing is going to move back and forth inside of its bore up and down. You've got another spool that's going to help in assisting the motion of another spool, they call a directional spool. And then we've got an unloading spool, sometimes called a bypass spool, that serves to block or allow flow back to the reservoir. And as far as the ports that are concerned, you've got one port that comes from the pump. This is the inlet port from the discharge of the pump. This port labeled as B, this goes into the pressure manifold, that goes to the accumulator. Then you got another port that they have labeled over here. This goes back to the reservoir. So you got three ports. So almost all every unloading valve that I'm aware of is gonna have to have at least a inlet, outlet, and a port that goes back to the reservoir. So let's take a look and see what's happened in the kicked-in position with the unloading valve. We haven't built up enough pressure in order to cause the unloading valve to go to kicked out yet. So the fluid flow from the pump pushes back against a check valve, an internal check valve inside of the unloading valve, and the fluid flow is allowed to fill the accumulator. So we're now building pressure in the accumulator. At this time also, the fluid flow has found its way underneath of a plunger that operates a pilot valve, but there's not enough pressure here, so the pilot valve stays in the position that you see it commanded to now. The pilot spool has got internal pathways or passages inside of it, and it's also got land areas. And what we do in this case, we're diverting some of the flow from the pump that's going around a hump of the unloading spool. It's going through a couple of areas of the directional spool. It's helping the hold the unloading spool in position to the right. It's also finding a pathway through the land area of the directional spool and pilot valve, and it's pushing or holding the directional spool in that position. Everything is now set up for kicked in. So again, until we build up to a certain point in pressure to cause this plunger to be pushed up, we're now filling the accumulator with fluid and we're building pressure on the circuit. Eventually, what happens is we reach a tipping point where we go to kicked out. This plunger is going to be pushed up. This now pushes the pilot valve up, and what that does is it now changes the flow path that's being provided to the directional spool. You can see what happens. The flow that's now being directed to the pilot valve is coming around the bypass spool. It's going around this way, and it has now pushed the directional spool in that position. And what the consequence of what this is happening, or what's causing it to occur, the flow from the pump is now provided with a pathway back to the reservoir. So okay, so the pilot valve is switched positions, the directional spool is swapped positions, and now we forced or biased the unloading spool or bypass spool, in this case over to the left. And what that does is it provides a path for the pump discharge to be sent directly back to the reservoir. So in theory anyway, you had taken the load off of the pump. And as long as the accumulator maintains enough pressure to hold this plunger up, you're going to stay in the kicked out position. You start to bleed off pressure from the accumulator by using a component. The plunger eventually is going to come back down again. The check valve will open and will deliver flow into the circuit, and we're going to build pressure back up again and eventually go back to kicked out. So it's kind of an interesting device. What I can tell you also with a lot of these unloading valves, there has to be a method for allowing these individual spools to move. So you'll see that, okay, we want to shift position from kick in to kick out. Well, there was fluid that was already trapped on this side of it. Well, how are you going to get rid of that? Well, there's usually in many of these unloading valves a port that will go back to the reservoir. This is what they commonly call a vent or a drain. And they specifically call it a drain in the Vickers manual. But the idea is, without that drain port attached to the unloading valve, there would be no way of venting or draining that fluid to allow motion for those individual spools to shift position. You know that liquids are considered to be what? Compressible. Very good. You've read my mind. Okay. So if you can't make the individual spools move to the new position commanded there, they'll stay in the position that they were in. So the purpose of that drain port is to prevent what we call hydrostatic lock. What it does is it allows that fluid to circulate back to the reservoir so you can shift position, either from kick in to kick out or from kick out back to kick in again. So that's what it does. Notice some interesting things too. The way it has to work. In any unloading valve, you've got common components. You'll have a check valve. You'll have something that will work as a pilot valve. You'll have something that will work as an unloading valve or a bypass spool. In the kicked in position, the flow from the pump pushes the check valve back and the accumulator is filled with fluid. At the same time, the bypass spool is closed and no fluid goes back to the reservoir. So if I were to ask you the position of particular valves that are, or components that are inside of the unloading valve. In the kick-in position, the check valve is open and the accumulator is being filled with fluid under pressure. At the same time, the bypass spool is closed. No fluid flow from the pump is going back to the reservoir. Okay? If we look at what's happening in the kicked out position, the accumulator is holding this check valve closed. It's aiding the spring, so the check valve is closed, but the bypass spool is what? Open. The fluid flow from the pump is finding a return pathway back to the reservoir. So check valve is closed, bypass spool is open. Just a picture that came out of the Vickers unloading manual to show you the component parts that you have. Check valve, you've got a pilot valve with a plunger beneath it in the side view. You've got the directional spool on the side of it. You've got the bypass or unloading spool located here. The big spring that works against the pilot valve is underneath a cap that's attached to the casting of the unloading valve. So that's what you have. Adjustments, well, bench adjustments, if you had to make an adjustment for minor variations of that spring compression, the Vickers unloading valve provides for the installation of shims that are underneath the cap. So if you have to make a minor adjustment for kick in and kick out, what you can do is add and remove shims as required in order to make minor adjustments. This is a bench adjustment, by the way, too. You'll notice that there is different part numbers of unloading valves, and whatever part number you have is pretty much guided by the type of or the compression of the existing spring that you have in the unloading valve. But we can't precisely control kick in and kick out just by, with a mechanical spring. So to provide for minor variations in compression, they allow an adjustment by the addition of a shim. Something also to kind of remember too, if you were to install shims as part of an adjustment, by necessity, you raise both kick in and kick out pressures. If you remove shims, you lower both kick in and kick out pressures. So it influences both kick in and kick out. And the differential is really controlled by the surface areas that you have inside of the valve itself or the components that are there. Okay. The test setup for a functional test at a bench, you have to replicate what the aircraft has for a hydraulic circuit. And it shows you the unloading valve, a gauge that you can monitor pressure with, an accumulator that holds the unloading valve in the kicked out position, and a kind of a calibrated leak that we can use to establish when the unloading valve goes back to the kicked in position again. But you have to have an accumulator to kind of be able to functionally check and adjust it for functioning. There's other types of unloading valves, but if you take a look at the piece parts inside of it, you can kind of figure out how it works without too much effort. They're going to have similar components. It's going to have a check valve. It's going to have something that will operate as a pilot valve. It'll have another valve that will operate as an unloading or a bypass spool. So even without the legend at the bottom for kick in to kick out, you know that the kick in position has to be what it is because in this case the check valve is open. The fluid flow from the pump is going where? Accumulating, okay? The bypass spool, the fluid flow from the pump, can it get by the bypass spool? No, so the reservoir is cut off. So we're in a position for buildup of system pressure. In this position, called kicked out, the check valve is closed. That means we've trapped fluid in the accumulator. There was enough pressure to raise this pilot valve in order to cause the bypass spool or unloading spool to open. And the fluid flow from the pump is circulating around the wasp waste area of the bypass spool and it's going back to the reservoir. But again, kind of the way that most of the unloading valves have to function. The spring that's on the inside of it, same thing as what you found inside of the Vickers type unloading valve. It works against the system pressure. You still have to have something that manipulates the bypass spool, but again, very similar to what you had in the Vickers. Be aware too, read the manual. Sometimes the adjusting screw, you would think by turning the screw clockwise that you might be increasing the kick in and kick out, not necessarily so. So just be aware that turning it one way or the other might do what you don't want to have happen. Adjustment on this type of regulator. Troubleshooting. I cover this pretty much in the checkout for the unloading valve and the relief valve. But regardless of the type of unloading valve that you have, there are some things that are kind of common to its operation. And if you have certain symptoms that are occurring, regardless of the type of unloading valve, they can pretty much be traced down to the same thing. So let's take a look at chattering first. Well, I've got low reservoir level. Okay, well, the chattering inside of an unloading valve might be due to the check valve moving back and forth too rapidly. So port A in the illustration is really the port that comes from the pump. If the reservoir level is low, you're going to be swallowing not only fluid, but also swallowing gulps of air from the reservoir being low. Every time that a gulp of air goes by that check valve, it's going to slam itself shut. So the first thing that I'm going to check in the event that you hear kind of a chattering effect, I suspect that probably it's going to be the check valve. What's going to be wrong is the fluid level on the reservoir is really low. So again, before you start looking at the unloading valve itself, look at the symptom, what it's doing. This is a good example too. The symptom manifests itself inside of the unloading valve, but the problem isn't with that. The reservoir level was low. Okay, so chattering check valve or chattering inside of the unloading valve, I kind of suspect that maybe the reservoir level is low. You're swallowing gulps of fluid that's causing the check valve to close itself off. Unloading valve cycles itself too frequently. Well, it goes from kick out to kick in, to kick out to back to kick in. There should be a certain period of time for normal cycling, whatever it is. It might be a half hour or whatever with no components being actuated, or maybe 45 minutes, whatever it's supposed to be. But let's say it cycles more frequently from kick out back to kick in again, maybe in half the period of time of where normally it's supposed to be at. What I kind of suspect then is you've lost the gas charge out of the accumulator. The device that was holding the unloading valve in the kicked out position was the accumulator. You have to bleed the fluid pressure off in the accumulator before it goes back to the kicked in position. So again, if the accumulator isn't functioning correctly, it'll cycle back to the kicked in position and eventually kick itself back out again. So check the accumulator before you do anything else. So another thing you might want to think about. Oh, by the way too, what is the normal cycle time? Well, that varies, This is a good thing to kind of know for a particular aircraft. What is considered to be the normal cycle time? Maybe the service manual might tell you what the normal cycle time might be. Okay, so you might want to investigate there. Accumulator doesn't charge with pressure. You've got zero system pressure. Well, if you can't get fluid into the accumulator, what that means is the valve or the unloading valve is somehow bypassing fluid. Well, what was holding the unloading valve in the kicked in position? Well, you got this big spring inside of it, okay? Well, maybe somebody forgot to install that spring. And if there's no spring inside of the unloading valve, the pilot valve is able to shift itself fully up, and immediately you'll go to the bypass position. So no fluid flow ever makes its way into the accumulator. All of the fluid flow is being diverted by the unloading valve back to the reservoir. It's possible you've got no spring inside of it, okay? Well, another thing too, maybe somebody has adjusted the relief valve in the hydraulic circuit so that the relief valve is completely open. So they backed off the big screw that's on the back of that ball, and again, the fluid is bypassing back to the reservoir, so that might be another thing too. So what I'm trying to tell you is you can't trap any pressure in the pressure manifold. But again, you might want to take a look at the spring. Is it there or not? Maybe the relief valve, in fact, is in the open position. That might have done it too. Okay. Let's take a look at another thing. Early kick in. Well, this is a little bit different than